and Dynamics에 대해서 이야기합니다. 박수로 환영해 주세요.
감사합니다. 1시간이죠. 1시간. Okay, I'll switch to English. So it has been a long time that I've been here, maybe 8 years or something. So it's a great pleasure to be here and to see old colleagues and some of the students. So today I will just survey what I did recently for several years. So I will not worry about details and any proofs. Okay, in geometric point of view, I'm concerned about some rigidity and deformability of some geometric structures. And usually geometric structures, there's some holonomy maps. So there's some Lie group and representation from a fundamental group of a manifold into some semi-simple Lie groups. So this is a very formal kind of approach, how to study rigidity and deformabilities and some dynamical properties of the action of automorphism group of the fundamental groups. So throughout the talk, G is a semi-simple Lie group and with a nice property. And one can form the collection of homomorphism from a fixed group gamma into G, and usually we quotient out by the action. It's a conjugate action. So there's some reason that I put 2 bars here, but don't worry about it. It's a geometric quotient. Usually it's just conjugate action. So by precomposition, automorphism group of gamma acts on this home gamma G. If you have some element from gamma to gamma, some homomorphism you can precompose here. But because here it's a quotient by inner action, inner automorphism of G, actually the action is outer automorphism of gamma. All the inner automorphism of gamma is kind of consumed inside this inner action of G. So there's a collection of homomorphisms, and this forms under the reasonable assumption this is a real algebraic variety. If G is a real algebraic group, this is a real algebraic varieties. So just imagine there are some manifold-like things. It might have some singularities and so on. So isolated point represent there's no deformations, right?
So is gamma just a group or?
It's some abstract group.
Discrete group? No.
Just abstract group. Usually it's a fundamental group of a manifold or a lattice in G. So isolated point mean up to conjugation is isolated, so there's no kind of one parameter family of these homomorphisms. So you cannot deform that homomorphism. And usually homomorphism represents some geometric structures. Okay?
The isolated point in where?
In chi, in character variety. So it's a one component. It's a one point. So it represents some representation from gamma into G, and up to conjugation, that's the only one. There's no nearby one because it's isolated, which means it's some kind of rigid object. Okay, then how can we distinguish some distinct components? And people study some geometric invariants attached to each component. And usually this geometric invariant is constant on component. So I will talk about maybe totally invariant a little bit. And especially when gamma is a surface group. So surface group means the fundamental group of a closed surface of genus at least 2. Okay? So it's a hyperbolic surface. Then there are rich theory about a deformation. So I will talk about when gamma is a surface group, there's some rich theory about moduli space, and we'll give some complete criterion of deformabilities. So it is called balanced conditions. And if you look at the dynamics of the outer automorphism group of gamma on this character variety, if there's some group acts on some object, you can ask whether the action is properly discontinuous or the action is ergodic. So people are interested for ergodic theorists, they want to find is this action is ergodic, or for topologists like me, I'm interested in the largest sum open set over which the action is properly discontinuous. So there's some theory about this. Usually in this case, I will restrict gamma to be a free group, and G to be a special Lie group, PSL to C, that is the isometry group of hyperbolic free space, and so on. And there are another kind of ergodic theory on each point of the character variety, and it has to do with some Apollonian sphere packings, but probably I will not have a time to talk about this one. So this is the sort of the synopsis that I'm going to talk about for an hour. So let me talk about rigidity side, isolated point. So there is some global kind of rigidity theorem which is famous in semi-simple Lie group theory. So if you have a two lattice, gamma and gamma prime, inside some semi-simple Lie group G, and if gamma and gamma prime are isomorphic as an abstract group, then Mastow, he proved that two lattices are actually the same up to conjugation. Okay? So lattice mean if you quotient out G by gamma, then the volume is finite. So Lie group has some hard measure, so you can compute the volume of the Lie groups. But before Mastow, André Weil, he proved some local rigidity phenomena about the lattices in semi-simple Lie group. So if you are not familiar with the lattices, you just imagine R2 and these integral points. The quotient is a torus. Okay? So if G is not locally isomorphic to SL to R, SL to R is a isometry group of the Poincaré disk, linear fractional groups. Except that case, he proved that every kind of natural embedding of the lattice inside this semi-simple Lie group is locally rigid. Okay? Gamma is included inside the G naturally as a subset. So it's a natural homomorphism. And if you try to deform it, if there's a one parameter family of this natural inclusion, actually they are all conjugated. So up to conjugation, this is kind of a trivial deformations. The way he proved this, that he used a group cohomology. So he calculated the first group cohomology of gamma with coefficient, the Lie algebra of the Lie groups. Okay, so this Lie algebra is a gamma modular under these adjoint actions. And what it means geometrically is that the H1, the first group cohomology, represent real Zariski tangent space of this character variety. Okay, even though it's not a manifold, you can easily imagine if there's no tangent space, it means there's no deformation, because usually the tangent space measured infinitesimal deformations. Okay, so that's the way how we prove this local rigidity. But unfortunately, usually the first group cohomology does not vanish for many groups and many semi-simple Lie groups. But there's some criterion to tell whether there's a genuine representation, genuine deformations or not. That the necessary condition is that if alpha is a non-zero element inside H1, for alpha to represent a genuine deformation, the bracket, this is a Lie bracket, so this is a 2-former with value inside the Lie algebra. This 2-former must vanish. So it's not a difficult fact, but this is a necessary condition. So the strategy is that...
What do you mean by deformation? So come back to T. So what is row 1?
Row 0 was a natural inclusion. So rho T is a one-parameter family of the homomorphisms. So starting from the row 0, there's a sort of one-parameter family of homomorphisms.
So you don't care about the final stage of it?
No, just locally. So because I'm interested in local rigidity.
Locally change
Yeah. When T is very small, so you try to deform. Imagine in R2 you have a regular kind of integral point where you can sort of slant this one, then it will give you, well, in integral you cannot kind of deform it. But anyway, so
T is also homomorphic.
yeah, rho T is a homomorphism. Yeah, collection of homomorphism nearby. And André Weil, he proved that they are all conjugate from the original one. So after conjugation, it's a kind of, there's no deformation. Okay. As I said before, if there's a lattice here, if you quotient out some symmetric space by this lattice, you have a manifold, a finite volume manifold. That means there's no kind of continuous deformation of this locally symmetric matrix. They are sort of isolated somehow. Okay. So feel free to ask any questions. If I can answer, I'll try to answer you. If you don't ask, usually people fall asleep because it's very dark. So let me try to connect up this kind of abstract language to some geometry here. S represents a closed surface of genus at least 2. So by uniformization theorem, if you give some complex structure on this surface, the universal cover is biholomorphic to the Poincare disk. Right? So there's a set of different complex structures. And each complex structure corresponds to a unique hyperbolic metric. And people call marked hyperbolic structures. And this is a type-null space. It's sort of a moduli space of hyperbolic metrics on the surface. And the set of moduli, the moduli space of marked hyperbolic metrics is equal to actually the set of discrete faithful representations like this up to conjugation. Okay. And it is known that the Teichmuller space is topologically homeomorphic to 6G minus 6 Arbor. And now you try to deform this one. One can deform, suppose a hyperbolic metric is given. That gives rise to a representation using a holonomy map. And now you try to deform a hyperbolic metric continuously, then you will have a continuous family of representations. Okay? But the target group here was PSL2R, but PSL2R is a subset of PSL2C, actually PSL2C. If you change the real number to a complex number, obviously it's a subset. But this guy represents the isometry group of hyperbolic 3 space. So here's a schematic picture. I have a hyperbolic surface, but now look at the quotient manifold in H3 instead of H2. And if you deform a little bit of this representation, it will give rise to some infinite volume hyperbolic 3 manifold. Okay? And people call it Quash-Fuchsian Kleinian group. And you can still further deform this Quash-Fuchsian Kleinian group such that it's more complicated. So it becomes doubly degenerate hyperbolic 3 manifold. But PSL2C, which is some component of SO41, this is included in PSPN1 for the larger semi-simple Lie group here. And this guy corresponds to hyperbolic, the isometry group of quaternionic hyperbolic space. Quaternionic hyperbolic space. So more larger. You take a larger semi-simple Lie group, larger and larger. And here's the schematic picture. So starting from hyperbolic surface, you can deform this guy, original representation, inside the bigger semi-simple Lie group. Then one can show that there's a geometrically infinite quaternionic hyperbolic manifold here, coming from deformation of the original hyperbolic surface. But somehow, because this is a larger symmetric space, it has a different geometric properties. Here, if you will not define what trigger constant is, but in this case, the trigger constant is 0. But this case, the trigger constant is always positive. Okay? So, depending on the embedding of this representation, the geometric taste actually varies. It's not a non-trivial thing. So don't ask me what trigger constant is. I can define it, but it's not necessary for us. So I just tell you, depending on the embedding, the geometric property changes. Okay, so here's a more kind of genuine picture about quasi-conformal deformations. So as I said before, starting from a lattice inside the G, one can take a bigger Lie group G prime containing the original one. And we know by André Weil there's no local deformation here, right? That was the first slide. André Weil, he introduced harmonic analysis to show this one. But I showed you already, if we enlarge this target group, there is a possible local deformation somehow. Okay? So we can ask, is this always possible? But the answer is no.
They're put into different
Right.
Geometry structures on what?
On the symmetric space associated to this semi-simple group. So, for example, if you have a hyperbolic surface, you can totally geodesically embed this hyperbolic surface inside hyperbolic 3
So
manifold.
in other words, quotient. is
Yeah, quotient.
like the-
Yeah.
it's become
The image.
I see. So there the geometry changes.
Yeah.
Okay.
You just,
Gamma is lattice in G, but not in G prime.
no, the quotient is an infinite volume usually. So is this always possible? And the answer is no. We are too optimistic. So the life is sometimes doesn't work very well that way. Because Margulis, he proved the super rigidity. If gamma was a higher rank irreducible lattice, even though you change the target group, there's no local deformation. So this comes from Margulis' super rigidity. Okay. So I will not explain what super rigidity, but there is an obstruction. So to play this game, we have to take a lattice which is not higher rank. So let's go to the rank 1 space. But
You have a G. And
Right.
You have so G and the gamma is.
a lattice here,
But the G prime can be very, very large.
it could be very large. Still, you cannot deform it locally. If G was a higher rank semi-simple group, so it's called Margulis super rigidity.
So
Super,
already
really
if G
super.
is big enough, then no matter how big you are embedding this into a group, still
There's no local deformation. So that's why it's called super rigid. So there are Lie groups which is not super rigid. So this is the only one actually. SON1, so it's an isometry group of real hyperbolic space. SUN1, they are isometry group of complex hyperbolic space. But even in SUN1 complex hyperbolic space case, there is no local deformation. So this is the symmetric space associated to this one is a Kähler manifold. Somehow there is a kind of a rigidity here. So I thought about in which cases we can prove more examples or what is the complete classification of the local rigid lattices and so on. And so far there are some examples like this. So gamma is a lattice, for example, in hyperbolic 3 manifold. You can embed this one in quaternionic things. There's still local rigidity. And here, this one is originally studied by Goldman and Milson, Toledo, and so on. But you can embed this one in a bigger Lie group like quaternionic. And these are all special kinds of Lie groups. U2 and 2, so 4 and 4, and so on. And the symmetric space associated to this one is called sort of quaternionic Kähler. It's very similar to a complex Kähler, but they don't have actually complex structure. So we found some examples like this. And somehow it wasn't that easy to prove these things. The local rigid lattices, except super rigid guys. Even I told you SON1, SUN1.
There is no local.
There's no local deformations.
examples.
Yeah. Even though these are not super rigid, still somehow the lattice is locally rigid somehow. So. I told you I will not care about the details of the proof. Let's talk about the geometric invariant a little bit. On the first slide, there was a character variety, and isolated points corresponds to locally rigid lattices. And there are a bunch of the other components. And how can we distinguish these components? So there's a one way. The typical way is if you have a arbitrary representation like this, because the associated symmetric space X, they are all k pi 1, you can always find row equivariant map from a universal cover M to X. Okay? There's no obstructions, because you see homomorphism gives you to define. They tell you how to define each loop goes where. You have to fill in the loops and higher dimensional cells. There is no obstruction. So once you define this row equivariant map, if X has some, for example, scalar form here, you can pull back this guy to here. And everything is equivariant, so the pullback form portion down. And by wedging with a form in M up to some power, you can integrate it over M. Okay, so you choose some appropriate K such that this form is proportional to the volume form, and you can integrate it. And one usually say this is a Toledo invariant, and one can show if you deform rho a little bit, this quantity remain constant. Okay. So on each component of the character variety, this number is a constant. So if luckily, if this invariant associate a distinct number to each distinct component, they will distinguish the component. But usually, it's not.
What is
Omega M here usually is a scalar form actually, defined on M. There is a scalar form omega on X. There is a scalar form. Not usually. People study complex geometry. But in my case, omega m is not actually a scalar form. Sometimes it's a four form or different forms. So when a manifold is a surface, this Toledo invariant is very special. The absolute value has an upper bound. This is known as a Milnor-Wood inequality. So Milnor studied this kind of circle bundle case long time ago. And it proved this number has absolute value has an upper bound in terms of just the topology of the manifold and the rank of the associated symmetric space. And somehow when this Toledo invariant realized the maximum, when this is equality, somehow this rho manifests a strong rigidity somehow. So they call maximal, when maximal Toledo invariant is attained, there is a rigidity phenomena. So the Toledo is a professor in Utah now.
Isn't that the name of the city?
Toledo is the name of the city in Spain, yes. But he is a professor. I think he's from South America somewhere. I forgot where he came from. So in higher rank case, there's some guys who studied this kind of things. When the Toledo invariant is maximal, is this rigid and so on. I guess I'm too slow. Let's skip this. And recently, one Swiss, one Italian, one German, they proved some strong property about maximal Toledo invariance. So in this case, we usually study surface group, and they study G Hermitian Lie group, such that because they need a complex analysis, they need a Kähler form somehow. So in this case, if the Toledo invariant is maximal, they proved the image of the representation is contained in a special Hermitian Lie group. Namely, it's called tube-type Hermitian domain. So the easiest example of the tube-type Hermitian domain is that the Poincare disk is biholomorphic to the upper half plane, right? Upper half plane. So upper half plane can be written as R plus I times half line. So this is the simplest tube-type domain. Okay? But usually tube-type domains are very special Hermitian domains. So somehow maximality of the Toledo invariant guarantee the image must be trapped inside this Hermitian Lie groups. So it's kind of a very strong phenomenon. And but the drawback is G is a Hermitian semi-simple Lie group. And recently with Pierre Pangxi, I proved sort of this is the only case. So the actual theorem is that now G is arbitrary semi-simple, not necessarily Hermitian. Then this representation phi is deformable in the sense of this definition. So deformable means I can deform a given representation to a Zariski dense one in any directions nearby. Then we call it deformable. So we found the complete criterion when this is possible. A given surface group representation into a semi-simple Lie group is deformable if and only if this guy satisfies some balanced condition. So it's getting more technical and technical. So I'll show you what's the story here. And using this one, one can prove sort of the converse of this theorem. So given surface group representation is always deformable to a Zariski dense one unless it's trapped inside Hermitian type domains. That's the kind of curl. Okay. I will talk about topology later. Handle bodies and Higard decomposition. So you can sleep until I reach. Because my background is three-dimensional topologist, and I don't know why I sort of drifted away to this semi-simple Lie group theory, but I'm always working on three-manifold. Oh, here. Yeah, I told you we found more examples here. The strategies, as I explained in the beginning, we decompose the Lie algebra into invariant kind of components. And the first component gives some trivial deformation due to André Weil. And there are some factors such that the first group cohomology does not vanish. Then we apply the necessary criterion. We will show that every non-zero alpha in H1, the Lie bracket does not vanish. I told you the necessary condition for deformation is that the Lie bracket should vanish. Okay. So there's a two-way to prove this thing. The first one is following the path of Andre Weil and Raghunathan, Matsushima Murakami, and so on. So if we follow their path, somehow the possible one form representing a possible deformation has a severe restriction. It turns out that alpha should be a holomorphic one form with value in very special Lie subalgebras. Okay, so you have to kind of go through the criteria and the work of Andre Weil and Matsushima Murakami. So once this is established, alpha is a holomorphic one form with values in special sub-Lie algebra. The proof is straightforward using Stock theorem. So Stock theorem is very important. The other way is using a high level. I think for me it's very high level because I do not understand the theory properly. We use Simpson's theory. So Simpson and the theory behind this is Deligne. So Simpson and Deligne, the algebraic geometers, they know them, but it's a little bit advanced things. They wrote many papers in IHS. I tried to read their papers. It is very difficult to follow their argument. But anyway, the strategy is using Simpson correspondence. So in short, what it means is that there's a character variety. So there's a collection of representations. And on the other side, there is Higgs bundle. Okay, whatever it is, there's a Higgs bundle, some special Higgs bundles. And Simpson, he proved there's a one-to-one correspondence as a set. Okay. So here I try to explain what Higgs bundle is, but maybe I'll skip it. The idea is in our case it's very simple actually. Suppose we have some reductive representation. Okay, reductive representation. Then using this reductiveness, we can form a K-principal bundle. And G has K is a maximal compact subgroup of G. So there's a K-principal bundle, and using basically Morley-Cartan form, graduate students, you should know what Morley-Cartan form. Using this, you can define the Higgs field. Okay, so there is some semi-stable Higgs bundle corresponding to reductive representations. One way is easy, and the other is a work of Simpson actually, because this is like a polystable Higgs bundle. Maybe Professor Park, he knows. No Higgs bundle. Okay. Oh, scary. This is the definition of Higgs bundle and Simpson. I will. So the global strategy is that given a possible deformation, there was a row equivariant map. And one can show this row equivariant map is actually a harmonic map if the representation is reductive. Okay? And if you want to use a complex geometry, for example, this is a quaternionic scalar. This is not at all complex scalar. You go upstairs. So usually people call this is a twistor space, but this is a very special case of Griffith periodic domain, whatever it means. Then we want to lift this guy, harmonic map, to upstairs. This process is called variation of Hodge structure. Okay? And in our case, this is non-abelian. So we have to prove there's a non-abelian variation of Hodge structures. And, and luckily, in our case, there's a work by Carlson and Toledo to guarantee the lift of this one. So every possible deformation, the upshot is that every possible deformation corresponds to variation of non-abelian Hodge structures. And then one can use some hypergroup cohomology calculation. So this is a sort of algebraic geometric way.
Which
Carlson, the Carlson who is doing harmonic analysis, I think it's Jim Carlson. So here, I have only 15 minutes. The flexibility criterion, so I'll tell you what the story is. So I told you for flexibility, the complete criterion is sort of balanced condition things. And usually people use the Kähler form. But in our case, there's no Kähler form. There's no complex structure. And how can we concoct available Toledo invariant in this case? And this is a kind of a brief way. So briefly, what it means is that you decompose Lie algebra using a center of the centralizer of the image. And each root space, so each decomposed component is called root space. Root space has a symplectic structure coming from this killing form. Okay, so once you have a symplectic structure, you can find a tamed almost complex structure. And if you have an almost complex structure, you can talk about Chern classes. Now you just evaluate fundamental class, this first Chern class, coming from flat bundle. And in that way, we can define Toledo invariant. And then we can use a signature formula. So this is a baby kind of application of Atiyah-Singer signature formula. So I'll skip and skip and skip. And look, there's a local.
Previous Toledo invariant uses the sum of some two forms and some forms.
So
you have symplectic form. Can't you do a similar thing?
yeah. You using symplectic structure, we can just.
You need the Chern class and the
You can just integrate complex the symplectic form actually. Yeah. So Simpson, he analyzed the local structure of these character varieties. So we use those kind of things to prove the balanced condition. So I even will not define what balanced condition means. So according to our criterion, we can test all the possible Lie groups. Okay. So case by case, we can go down the list when the surface group is rigid or flexible. So for classical simple Lie groups, we finished. So this is the only kind of rigid case. Except this, everything is flexible. Okay. And there are some issue about global rigidity, like Masdal rigidity. And I found out the global rigidity has to do with some Gromov simplicial volumes and so on. Let me talk about a little bit of dynamics on the character variety. So as I promised you, the group here is a free group with n generator. At least n is equal to greater than or equal to 2, such that it's not abelian free group. and the target Lie group is just the PSA to see very special case. Then, so the people who knows about the hyperbolic structures, so in this case, the Schottky space forms some open set of the character varieties, open set. One can show the outer automorphism group of the free group acts properly discontinuously on this Schottky space. But recently, Minsky, he defined the primitive stable representation. So all the Schottky groups are primitive stable. And he found he defined the larger open set of the character variety, of which the outer automorphism group acts properly and discontinuously. So maybe I will define what the primitive stable representation means, because it has to do with the geometric group theory. So a word in free group is primitive if we can complete it to a free generating set. Okay? So for example, AB is a free group 2, the generator of the free group with 2 generators. A square is never primitive. You cannot complete as a free generating set using A square. Okay, so primitive is one of the generators. Then you form a Cayley graph of this free group, which is a tree. Okay, Cayley graph. And you can define the orbit map for each element here. So here's a Cayley graph. Here is H3. Fix some origin in H3. If you have a word here in Cayley graph, each vertex corresponds to a word, an element of a free group. So via this representation, it's some isometry element in H3. Because rho is a representation. Then you send this origin to that point, and you connect this orbit by broken geodesics. So you embed Cayley graph inside H3 using this orbit map. Primitive stable means this. Oops. Primitive stable means, here I try to, so this is the Cayley graph of the F2. So take a bi-infinite geodesic in the Cayley graph corresponding to a primitive element. So for example, A is a primitive element, then the corresponding geodesic is just this horizontal one. Identity A square, A inverse, A to the minus square, and so on. There's a bi-infinite geodesic in the Cayley graph. And you map this thing via this orbit map to the sequence of broken geodesics. Then one can see that every image is a quasi-geodesic. It's almost a geodesic. But it could be very deviated from actual geodesics. So there's a measure how much deviate this quasi-geodesic from being a geodesic. It's called the quasi-geodesic constant. So primitive stable means this deviation should be uniformly bounded. Okay? Every image of the primitive geodesic from a Cayley graph should be mapped to a quasi-geodesic, which is uniformly deviated from a geodesic. So quasi-geodesic constant should be bounded uniformly. Then one can easily see that the Schottky space satisfies this thing. Actually, the entire image is quasi-geodesically embedded in H3 for convex co-compact Schottky space. And So it has to do with some three-manifold theory. We completely characterize which representations are primitive stable in high public three-manifold. The summary is that either, so we always, because we know Schottky group is always primitive stable, we have to deal with geometrically infinite high public three-manifold. So either there's no parabolic, or if there's a parabolic, then we say each component of the parabolic locus or a component of the ending lamination should be disk busting. So this is a Kleinian group theory. So there is a complete criterion of primitive stable representations in high public three-manifold. Okay. So I will skip the proof and everything. Let me talk about the handle body because I'm not familiar with this thing. So there's some possible application. Minsky asked whether there's a primitive stable closed high public three-manifold. Because all the examples so far is infinite volume high public three-manifold. But is there any closed high public three-manifold which is primitive stable? Here's a one way to construct infinite family of closed high public three-manifold, which is primitive stable. Closed, compact, and no boundary. Yeah, closed. So the way to deal with this, every high three-manifold has a Higard decomposition. Okay, so the group factor through like this. Start from a free group, which is a handle body. By attaching another handle body on the other side, you can kill existing non-trivial element here. So it gives rise to some relations. So this is originally there was a representation from pi 1 of m into PSL to C, coming from high public metric. And here you can make it factor through like this. Just restrict the fundamental group to one side handle body. And if this is primitive stable, we say the closed three-manifold is primitive stable. The upshot is here, the older work is to show if there is a sequence of high public three-manifold such that such that the limit representation is primitive stable, then all the nearby guy is primitive stable by openness of primitive stabilities. So this is the most difficult kind of a task to show there's a limit, algebraic limit of this thing. And how do you show there's an algebraic limit? Then we use this Morgan theory. If it diverges, then it acts on R3. Then we drive a contradiction things using the Gromov's idea. And after this, I'm asking whether is this a genuine kind of phenomena? Is this a general situation? There's a notion of the Higard distance for Higard decompositions. Okay, so I'm asking if the Higard distance is large enough, does it guarantee that the three-manifold is primitive stable? This is my questions. And
so could you tell me what's the definition of primitive stable again?
Primitive stable means there's a K-graph of the fundamental group. There's an H3, so you can map this K-graph into H3 using orbit map. Then you pick any bi-infinite geodesic here in K-graph corresponding to a primitive element. And you have here quasi-geodesic as an image. But quasi-geodesic has a quasi-geodesic constant, which means how much it deviates from actual geodesics. And we require, independent of the chosen primitive element, this quasi-geodesic constant should be uniformly bounded. That's the definition of primitive stable things. And we tested for closed three-manifold case using pseudo-Anasov map. And is it possible to generalize this kind of thing to arbitrary high Higgs distance? If the Higgs distance is large, does it guarantee that the three-manifold is primitive stable? And I have no idea how to prove these things. So if you know Higgs distance and Higgs splittings, please tell me. Okay, I will stop here. Thanks for your